The Constitution of India, Preamble. We, the people of India, having solemnly resolved to constitute India into a sovereign, socialist, secular, democratic republic and to secure to all its citizens justice, social, economic and political, liberty of thought, expression, belief, faith and worship, equality of status and of opportunity, and to promote among them all fraternity, assuring the dignity of the individual and the unity and integrity of the nation. In our Constituent Assembly, this 26th day of November 1949, do hereby adopt, enact and give to ourselves this Constitution.
Happy morning, students. So we have completed till our heterogeneous equilibria with Le-Chatelier's principle and effect of concentration, pressure, temperature, catalyst and inert gas. Today we will be focusing on ionic equilibrium, because when we talk about equilibrium, I told you it's a stable state condition where here the reactants and the product concentrations are in constant. So that is how we were deriving Kc, Kp, equilibrium constant and at constant pressure. So what is ionic equilibrium? Now what happens when you take an aqueous solution of sugar dissolved in water? You will see, children, it do not conduct electricity. But then if I am going to take an aqueous solution of common salt, that is our sodium chloride, what happens? It will definitely conduct electricity. Salt water conduct electricity. Now what is the reason behind that? Salt is nothing but sodium chloride. Sodium chloride, when dissolved in water, it is going to be dissociated into Na plus and Cl minus ions. Now these ions are responsible for the conduction of electricity. So there was a scientist, Michael Faraday. Now he, after experimenting several salt and several solutions and substances, he then came into a conclusion. He said there are substances which may conduct electricity, which may not conduct electricity. So he classified them into two types. The first type they are called as electrolytes and the second type are called as non-electrolytes. Electrolytes are substances which allow the electric current to pass through them or which conduct electricity. 10th standard you would have studied in electrolytic cell. Children, if you can recollect, we were studying acid, bases and salts. They are used as electrolytes. So here electrolytes are those which conduct electricity. Non-electrolytes are those which do not conduct electricity. Now electrolytes were further classified into strong electrolytes and weak electrolytes. Strong electrolytes are those which undergoes complete ionization. I would say 100% ionization happens there. See, when I take sodium chloride in water, definitely all the sodium changes into Na plus, all the chlorine changes into the negative ions. So that is what is a complete ionization. But what happens in the case of weak electrolyte? In weak electrolyte, let me take acetic acid, it will dissociate into acetate ions. There will be some acetic acid also present. We may not be getting complete ionization. There is only a partial ionization. We call it as 50% ionization. So NaCl gives a 100% ionization, acetic acid only a 50%. So when you take acetic acid situation, there are ionized ions, there are unionized ions also present in the solution. So there they form an equilibrium. Equilibrium happens anywhere. So there an equilibrium is developed. It is going to be started between whom? It is going to be between the ionized ions and the unionized ions. So the ions and the unionized ions, only between the ions there is going to be an equilibrium. Such an equilibrium we are going to define it as ionic equilibrium. So ionic equilibrium is that state of equilibrium which exists between the ionized and the unionized ions. So now I think you would have understood about electrolytes and non-electrolytes. We are going to start with acid, bases and salt. We know what is an acid. Acids are substances, acidus, we have learnt right from our 8th, 9th standard, I hope. Acids are those which are acidic or have a sour taste. Like I can say citric acid present in lemon, ascorbic acid in orange, tartaric acid in tamarind. So acids actually they turn the blue litmus to red. They have a pH less than that of 7. We say acidic in nature. They produce hydrogen gas or they liberate hydrogen gas when they are dissolved in metals, when they react with metals. You would have studied the reaction with magnesium, how magnesium with HCl gives MgCl2 plus liberation of hydrogen gas. So anything that can give H plus ion or liberates hydrogen gas, they are called as acids. Now what are bases? Bases are bitter in taste. They are soapy to touch. And then what? They turn the red litmus blue. They have a pH of more than 7. And then you would say they produce hydroxyl ion, OH minus ions are produced by bases. Now when this acid is going to combine with a base, it is going to form a salt. Now that is how we know how sodium chloride is developed. Sodium hydroxide, when it is combining with HCl, it gives sodium chloride plus water. So this is a strong base, this is my strong acid, and this is a salt that we get when an acid combines with a base. So these are acid, bases and salt. But now what are we going to see here is different definitions of acids and bases from Arrhenius theory, Bronsted theory and Lewis theory. So these are the 3 things which we are going to see now with definition of an acid, base and salt. We are going to now see the sodium chloride when it splits into Na plus and Cl minus. In the solid state there is an electrostatic interaction that is holding this Na plus and Cl minus together. Because these are positive and negative charges, so the opposite charges are held closer. Now we know water is an universal solvent having a dielectric constant of 80. What is dielectric constant? The amount of potential energy which is stored under the action of electric field. When there is an electric field passed, the amount of potential energy that the substance can hold. So this electrostatic interaction force is actually inversely proportional to dielectric constant. So what happens when sodium chloride is dissolved in water? The electrostatic force of the sodium chloride actually decreases because of the increased dielectric constant. When this is more, this becomes less. So that becomes reduced. So the interaction force becomes weaker. So sodium chloride will easily break into Na plus and Cl minus. Any bond that you take, whether it's a polar bond or a non-polar bond, the extent of ionization actually depends on the strength of the bond, how powerful the bond is, whether it can be easily broken or it is difficult to break the bond. And it also depends on the extent of solvation, whether 100% ionization is there or whether only 50%. What is solvation? Dissolving the solute in a substance, in a solvent. Now there are 2 factors like the dissociation and ionization. We know what is ionization, where a neutral molecule split into its ions in the solution. But what is dissociation? It is the separation of ions in the solid state. That is, the solid state of the molecule actually breaks into its individual constituent ions. That we call it as dissociation. So now if you have understood about ionic equilibrium and how does the extent of ionization helps in forming a solution. Now we will get back into Arrhenius theory. Yes, now we are going to see about the definition of an acid base with respect to Arrhenius theory, Bronsted theory and Lewis concept. In Arrhenius theory, he says acids are those which can produce H plus ion and bases are those which can produce OH minus ion. So if take an acid HCl, it gives H plus and Cl minus. That HX again when it dissolved in water, it gives a hydronium ion. Now why this is happening is because the H plus that is present in an acid is an active proton, which immediately combines with the water to form a trigonal pyramidal structure which is called as an hydronium ion. So this hydronium ion is more active, and that's why it is immediately formed when an acid is dissolved in water. So that is how when an H plus or H3O plus is being given, it's called as an acid. In case of base, it produces hydroxyl ion. But whatever is being produced hydroxyl ion, certain substances are also called as bases, though they don't have this OH group. Like ammonia, we have been learning that ammonia is called as a base but does not have an hydroxyl group. We just say because nitrogen has got a lone pair of electrons, so that's why it is called as a base. Now whose theory is going to predict that ammonia is going to be called as a base? Now we will see. Here in Bronsted-Lewis theory, it says acids are those which can donate H plus ion, bases are those which can accept protons. When I say proton, it is nothing but H plus. So if you take an example, ammonia when dissolved in water, here ammonia is going to act as a base and water is going to act as an acid, because you see ammonia adds one proton, it accepts a proton because bases accept proton. So ammonia is going to accept a proton and becomes ammonium ion. The ammonium ion which is formed by accepting the proton, that is the base which accepts a proton, becomes an ammonium ion, is called as a conjugate acid. It is called as a conjugate acid. If you see this base ammonia and this conjugate acid ammonium, they differ by only one proton. This is NH3, this is NH4 plus. Only one hydrogen is more in this conjugate acid. Then next, when you see water, it is losing a proton to become OH minus. So water acid which loses a proton to become a conjugate base, which is OH minus. So there you can see again this acid and the conjugate base also differs with one proton. Such pair, acid base pair, which differ by one proton, we are going to call as a conjugate acid base pair. Conjugate acid base pair where they differ by only one proton. So here I can say ammonia and NH4 are conjugate acid base pair. This is conjugate acid, this is base, and again I can say water and OH minus are again conjugate acid base pair. This is an acid, this is a conjugate base. So for every base you get a conjugate acid, and for every acid you get a conjugate base. Next comes the Lewis acid. In Lewis acid, acids has got a definition of accepting an electron pair, and bases has got a definition of donating an electron pair. If you remember children, in chemical bonding chapter we learned BF3 does not obey the Lewis octet rule because incomplete octet. So BF3 needs a pair of electrons, so it is a Lewis acid which is obtained from ammonia which donates an electron. So ammonia is called as a Lewis base and BF3 is called as a Lewis acid. So aluminium chloride, carbonate ion, these are also called as Lewis acid, and water, ammonia, these are called as Lewis base. Now we have completed till this. Now we will be getting into ionization of acids and bases, and then we are going to learn about the ionization constant. pH will be doing once you come here, where we are going to see the problems of how to solve and find out the pH of the solution. Then we will be getting into ionization constant of weak acid and base. We are going to see about ionization constant of water, weak acid and weak base. We know what happens with water. Water can act as an acid, water can act as a base also. So what happens when water and water, that is in water, when the solution is going to be mixed, there is going to be a dissociation happening with the formation of a hydronium ion and hydroxyl ion. So here my water acts as an acid and I get a conjugate base. Water can act as a base, I get a conjugate acid by accepting a proton and losing a proton. So if I am going to write the equilibrium constant for water, that is Kw, that is equilibrium constant for water, how do I get it? I get it as H3O plus into OH minus, product of the concentration of the product divided by the reactants. But we know for pure solids and liquid the equilibrium constant does not change, the concentration do not change. So, the equilibrium constant for water, that is H2O, is actually H plus and OH minus, where through experiment conditions it was found that the concentration of H plus is 1.0 into 10 power minus 7. So, when I am going to consider two molecules of water with H3O plus and OH minus, it is going to be the double of H plus concentration, which is 1.1 into 10 power minus 14, that is this raised to the power of 2. So, I get 10 power minus 14 m square. So, this Kw is very important, where we will be using in almost all the situations. But now we are going to see the ionization constant of weak acid. Whenever I say weak acid, we know it only partially dissociate or ionizes. So, what happens here, when HX is dissolved in water, a weak acid when it dissolves in water, it forms a hydronium ion and X minus. So, here when HX is just getting dissolved, it forms H plus and X minus. So, the initial concentration, let it be C, that is C, and here only the reactant concentration is not changing because the products are not formed. So, here we consider it as 0. So, let alpha be the extent to which HX completely ionizes, but actually the ionization is not happening completely, only partial ionization is there. So, that becomes minus C alpha, because there is a decrease in the concentration of the reactant and increase in the concentration of product. So, this becomes minus C into alpha, which is the extent of dissociation. Here this becomes plus C alpha and plus C alpha. So, when there is an equilibrium achieved, it will be the whole concentration C minus C alpha, and this is the C alpha during equilibrium. So, how do we write Ka? Is the product of the concentration of the products divided by the reactant. On solving, I get C alpha square by 1 minus alpha. So, in case of an acid, I get H plus X minus by Hx, where this is called as Ka, equilibrium constant of an acid. In your textbook, it will be given pKa is equal to minus log of Ka, where we will be doing problems in the class. But you should be knowing, when we get a value for the equilibrium constant of an acid, the greater the value of Ka, the stronger will be the acid. But how do we find whether it is acid, base or neutral? Only with the equilibrium constant of water, because if the concentration of hydronium is greater than OH minus, it is an acid. If it is equal to OH minus, it becomes a neutral. If it is less than OH minus, it's become a base. So, that is how we find out an acid, base and the neutral compounds. Then we take the equilibrium constant or the ionization constant of an acid and a base. When I take a base compound, any hydroxide splits into M plus and OH minus. Taken into consideration equilibrium constant of base, that is Kb, we get M plus OH minus by MOH, where again the same extent of dissociation. So, C alpha square by 1 minus alpha, pKb equal to minus log of Kb. So, these are the things which comes under ionization constant. So, here children, in your textbook we have steps in determining the equilibrium constant. Now, we have the relation between Ka and Kb. With that, we will be getting into ti and polybasic acids and common ion effect. Okay, children. Now, we are going to see the relation between Ka, Kb with Kw, that is equilibrium constant of an acid, base with water. What happens here, if you see, ammonium ion, when it is dissolved in water, it gives hydronium ion and releases ammonia. So, the equilibrium constant of an acid is given here. Similarly, when ammonia is dissolved in water, you get ammonium ion and hydroxyl ion, where equilibrium constant of a base is given. Now, what happens is, when you have too many steps involved in a reaction, the net equilibrium constant of a reaction can be given by the product of all the equilibrium constant of the reactions. That is, on an average, I can say Kw, equilibrium constant of water, will be equal to the product of the equilibrium constant of an acid into its base. So, in general, we can write net equilibrium constant will be equal to K1 into K2 and it goes on. So that is how we write the relation between Ka, Kb and Kw. Now when we talk about dipolybasic and diacidic, polyacidic, which means when we know an acid can donate only H plus ion, there are polyacids or polybasic which can donate more than one OH minus or one H plus ion. So like I can say oxalic acid, phosphoric acid, they can donate many, carbonic acid, they can donate more than one hydrogen ions. So when you take H2X, the first step involved is release of one proton and HX minus. Now this HX minus is now a negative ion. To remove the second proton from this negative ion is not that easy when compared to that of a H2X. So from HX it becomes H plus and X2 minus. So when I write the equilibrium constant of an acid for the first reaction, the product of the concentration of this product divided by the reactant, and for second one it is the product of the concentration of this product divided by the reactant. So here I would say Ka2 will be lower than Ka1. That is, the higher order ionization constants are lower than the lower order concentration. So I can say Ka1 will be the highest, then comes the next and the next. So this is what is dipolybasic and dipolyacidic substances, right? When we are studying about this acids and base, definitely strength plays an important role. How do we say it is good acidic or highly acidic? If the energy required to break the bond is less. If the bond strength is less, it is easily breakable and the acid strength increases. Similarly, the polar covalent nature. If there is more covalency, the electronegativity is more. More electronegativity, the bond strength is less. So what happens? The bond can break easily, the acidic strength increases. Or I can say when we go down the group, the size of the halogen atom increases actually, or any electronegativity atom, it is attached along with hydrogen, it increases. So when it increases down the group, the bond strength actually decreases. So it is easy to remove or to break the bond with less energy, so more will be the acidic strength. And last but not the least, if you say for methane and other thing, the covalency, that is the covalent character actually differs when you go from methane, ammonia, or when you talk about H2O or HF, what happens? There is a difference in the electronegativity of the carbon and hydrogen, fluorine and hydrogen. So that is how the acidic strength plays an important role in the covalent nature and the bond strength and also the electronegativity. Next, we are going to learn about buffer solution, common ion effect. And regarding solubility product, once you come here, we will be solving the problems with examples that is there in your textbook and also the previous year's questions. Now we will see what are buffer solutions. See what are buffer solutions. Buffer solutions are those solutions which can resist the change in the pH when an acid or an alkali is added into it. Any acid or alkali is added, we know what happens to the solution. It gets disturbed, that is the pH may vary. It can become more acidic or it can become less acidic, it can become more basic or it can become less basic. But buffer solutions are those which are added, or it's a mixture which are present in the solution which will resist, which does not allow the pH to change. It remains constant. Examples we have a buffer solution made up of a mixture of acetic acid and sodium acetate, which is a salt of the acid with a strong base. The base is used is here sodium hydroxide. So weak acid is acetic acid, its salt is sodium acetate, the base used here is sodium hydroxide. Another mixture of buffer is ammonium hydroxide with ammonium chloride, where you have a weak base ammonium hydroxide, its salts ammonium chloride and a strong acid HCl. So these mixtures are basically classified into two. If you want to make the solution as an acidic buffer or you want to make it as a basic buffer. If it's an acidic buffer, you have a combination of weak acid, strong base and the salt. If it's a basic buffer, a weak base, a strong acid and the salt. So the pH value will be less than 7 for an acidic buffer, it will be greater than 7 for a basic buffer. Too many things are given in the textbook. This is a comprised one which I have given you. Learn one example of each of the buffer solutions. So this buffer capacity is nothing but to maintain the constant pH value in the solution. That is the number of moles of acid or buffer which are required to change the pH of 1 liter of the solution and maintain a constant pH. So this we call it as a buffering capacity. Here in buffer solution, before getting into the buffer solution, we also have an important thing that rules this any solution is a common ion. We know when a solution, a reaction is happening, say an acetic acid give H plus and CH3COO minus, there is a shift in the equilibrium when you add an ion, that is H plus. If it is going to be added more, what will happen? The reaction will move towards the acetic acid because of the common ion which is already present in the solution. So any addition of a common ion or an ionic species that already exists in the solution, we call that shift as a common ion effect. And here we are going to learn also about hydrolysis of salts and pH. Any acid, any base, it can be a weak acid strong base, can be a strong acid weak base, it can be a weak acid and a weak base, or what happens is there is a salt that is formed. Now let us consider 3 cases where we have a weak acid and a strong base, CH3COONA. CH3COOH is a weak acid, the base NaOH is a strong base. So when this is getting mixed, NaOH being a strong base ionizes completely. NH4Cl, a weak base and a strong acid HCl, HCl ionizes completely. Now when you take a combination of weak acid and weak base, CH3COONH4, there you can see the ionization is a little bit different because both are weak. So there is a partial ionization happening. So here I want to tell you, any hydrolysis of the salt is independent on the strength or the concentration or the pH value. So here I can write pH of the whole salt can be determined by 7 plus half into pKa minus pKb, where pKa is the pH of the equilibrium constant of an acid and a base, which is given to you in the textbook. You can mark it now only, children. Page number 226, if you can see pH of the solution they have given 7 plus half into pKa minus pKb. If it is greater than 7 and if the difference is positive, it will be less than 7 if the difference is negative. So we will be doing every problem in the class in May, so you do not have to worry about it. And we also be doing this solubility product in the class, because if I am going to explain solubility product without doing the problem, that may not be effective, but definitely I will be including videos for you to understand much better. Now whatever happens in the class, try to make sure that you take notes or you mark in the textbook wherever it is necessary, because this lesson we have more and more of problems which we will be doing into the May month. Okay. So with this chapter is getting over, and I will be putting the videos, solubility product and equilibria we will be discussing in the class definitely, and the other problems also, the solved problems in the textbook we will be doing in the class. Okay children, have a great day, take care. If you have any doubts, do call me, we will be doing it, or mark it in the textbook, we will be doing it once we meet here directly. Thank you, take care, bye.